In this video, I'm going to present the solutions of the review problems that were presented in class. These problems come from page 297 and 298 of the textbook and can also be found on the ebook. First, problem number 47, we had 48 numbers, and what was given was, more importantly, that the 48 numbers had the following properties: that the sum of the numbers was equal to 387.8, and that the sum of the squares worked out to be 4,247.08. Okay, and for part A, the question was to estimate the true average bond strength in the way that conveys information about precision and reliability. In other words, the true average bond was the population mean, and the question is kind of open-ended, but states to find a confidence interval. And the percentage is not given, so it's free to interpretation using your best engineering judgment as to what percentage makes sense. So in class you might have chosen a different percentage. In the video here I'll use the 95% confidence interval, but you could have done something different in class and would be entirely reasonable. So to do the confidence interval we need x bar, and x bar will be equal to the sum of the entries divided by the total number of entries, and you see there's a 6 by 8 grid of entries, so 48, and so that works out to be 8.07917. To get the standard deviation, there's the formula that was presented in class, and we also discussed this, I think, about the second week or so of the semester, that S is equal to big square root the sum of the squares, 4247.08, minus the sum squared divided by 48, and then the whole thing divided by 47. And this worked out to be approximately 4.86844. Okay, and then we're going to figure out the test statistic. Now I'm going to do the test statistic in two different ways, mostly to show that there's really no big difference between the two techniques. We have 48 observations, and so using simply the bell curve is a completely reasonable thing to do. So let's first do it with the bell curve. So bell curve, we have, picture goes like this. 95% confidence interval was what I chose, and we'll choose that to be in the middle. And so that leaves 0.025 on this side, and of course 0.025 on the other side, so there's a combined 0.975 for the two areas. And so either using Excel or else the table or else your calculator, you can figure out the 97.5 percentile, and that works out to be 1.95996. And so using this information, the 95% confidence interval works out to be the mean, 8.07917, plus or minus 1.95996 times S, which is 4.86 or 0.86844, divided by the square root of 48. And that works out to be 8.07917 plus or minus 6 point, plus or minus 1.37726. So that's using the bell curve. It also can be done using the t-distribution. It's never wrong to use the t-distribution if you're given the sample standard deviation. Then what we have is the sample standard deviation, not the population standard deviation. So if we have the sample standard deviation, it's never wrong to use a t-distribution. So let me do this now a second way, assuming that this is a t-distribution. And in this case, I would have n minus 1 for 47 degrees of freedom. And so doing the tip in the calculator, instead of having this test statistic, we would have something that's a little bit different, 2.01174, using 47 degrees of freedom. And so if we use this technique, we would have 8.07917 plus or minus 2.01174 times S, 4.86844, divided by the square root of 48, and which gives a slightly different margin of error. So 8.07917 plus or minus 1.41365. Okay, so you notice that there is a difference. However, there's no practical difference. The measurements themselves were only given to one decimal point in the first place. So 11.5, 12.1, 9.9, 9.3. If you look at the numbers in the textbook, all the numbers are given the lowest numbers in the tenths digit. So if we round these off to tenths, this would be 8.1 plus or minus 1.4. This would also be 8.1 plus or minus 1.4. So practically speaking, it makes no difference whatsoever if we have the t-distribution or the z for solving this problem. So, but I did want to present it both ways just for the sake of completeness. During class, a few people asked me about part B for the proportion. For part B, you have to do this one that's similar to number 51, which we'll do in a few minutes. There are 48 measurements, and then you simply have to count the number of measurements that are greater than 10. So doing that real quick, as just looking at the paper, I see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 out of the 48 are bigger than 10. So your p hat would be 12 divided by 48, which is 0.25. And then you proceed in very much the same way as we'll do number 51. So that's the way that you would do part B, because it is a proportion problem. Okay, so that's number 47. Number 48 is going to be a little bit less work, actually significantly less work. Number 48, we have, let me write down the information. We have a sample of size 9. So we're going to have 8 degrees of freedom. The sample mean is given by 188.0. And the sample standard deviation is 7.2. And the question is to construct a 98% confidence interval. So we draw the picture. It's 98%, and unless it says otherwise, it's going to be two-sided, so 0.98. And so what I need to find out is the 99th percentile of the distribution. So again, there's 3 ways that this can be done. You can use tinv or t.inv, pardon me, on Microsoft Excel, or inv-t on a TI-84 plus or higher. And just remember that's the 99th percentile for this picture. If you're using the table, the number, and we're using the table that's in the textbook has a table so that the area to the right is the number that appears on top, so 0.01. So either way, we get, and also we have 8 degrees of freedom, because n minus 1 is equal to 8. And so we work this out, and the test statistic worked out to be 2.89649. And so our 98% confidence interval will be 188.0 plus or minus 2.89649 times 7.2 divided by the square root of 9. And that works out to be 188.0 plus or minus 6.9515 So that's to, the mathematical answer. Now, using engineering judgment, we see that everything is cut off to the 10th decimal place again, one extra decimal place, and so we probably would report this as 188.0 plus or minus 7.0, rounding off. But it's always safe to round off at the end as opposed to at the beginning. Okay, so that's number 48. Number 50 is more of a conceptual problem. So let me draw the picture that goes along with this conceptual problem. So we have a confidence interval going from 229.764, and on the other side we have 233.504. And the question, that's the 95% confidence interval. And the question is, if that's the 95% confidence interval, and the sample size is 5, that's important. If that's the 95% confidence interval, then what is the 99% confidence interval? Okay, so to do that, first we remember that the mean is always going to be at the midpoint of any two-sided confidence interval. So just taking these two numbers, adding them up, and dividing by 2, we get that the midpoint of this confidence interval is at 231.634. Then the margin of error will be the difference between the right endpoint and the midpoint, or else the midpoint to the left endpoint. So just doing the subtraction, we find that the margin of error for this problem is 1.87. Now the margin of error is also equal to the t statistic, the critical value from the t distribution, times s divided by the square root of n. Now this is a 95% confidence interval, so drawing the t distribution, 95% of the area is in the middle, so that means 2.5% lies in the left tail, or else, and also 2.5% lies in the right tail. So we have the option of finding the 97.5 percentile using technology, or else using the 0.025 column in the table in the book. And we remember that the degrees of freedom is going to be equal to 4. And so working this out, the test statistic here works out to be 1.50604. Sorry, that's the final answer. I'm looking at the wrong page of my notes. The number here works out to be 2.77645. So 1.87 is equal to 2.77645 times the s, which is unknown, divided by the square root of 5. And so s is equal to what I just said, 1.50604. Okay, so that's the information from the 95%. Now we get to work on the 99%. So the 99% confidence interval will have a similar looking picture. 0.99 in the middle, 0.005 in both tails. So I need to find either the 99.5 percentile using technology, or else use the 0.005 column in the table. And we find this critical value to be bigger than 2.77, not surprisingly, and that works out to be 4.60409. So finally, the 99% confidence interval is going to be the mean 231.634 plus or minus 4.60409 times s, 1.50604, divided by the square root of 5. And that works out to be 231.634 plus or minus 3.101. And not surprisingly, this 99% confidence interval is going to be a bit wider than the 95. 231.634 plus 3.101, that's 234.735. So that's going to be out here someplace. Okay, and if I subtract, I would get 200 and I believe 28.503, and 228 is going to be out here, so that's over here someplace. So not surprisingly, the 99% confidence interval between the two parentheses in red is bigger than the 95, which was marked in black. So just to check that the answer, passes the common sense test. Okay, so that's 50. Number 51. This is a confidence interval problem. So the information from the problem is that we have n equal to 2,253. The value of p hat is equal to 1,262 divided by 2,253, and that works out to be approximately 0.56004. So the q hat will be equal to 1 minus p hat, so 0.43996. And the last thing that we need is the z value. We're looking in this problem for a 95% confidence interval. And so drawing the picture over here, you probably know the answer by now, but let me draw the picture anyway for the sake of practice. We have 0.95 in the middle and 0.025 in the left tail and 0.025 in the right tail. And so we're looking for the 97.5 percentile off the bell curve. And it's important that we're using the bell curve. So this is an important point. It's a proportion problem, and so because it's a proportion problem, that we automatically use the bell curve. We only use a t-distribution when it's a problem concerning an average and we have a sample standard deviation and usually a small sample size. This problem is a proportion problem, and the proportion problem, it is automatically using the bell curve because the bell curve approximates the binomial. And so the number here works out to be our friend 1.95996. Okay, so then it's just a matter of plugging into the formula. P tilde works out to be, let me write out the formula, p hat plus z squared, where z is 1.95996 over 2n, and n of course is up here, divided by 1 plus z squared over n. And then we plug this into the calculator very carefully, and once again we get 0.56004. And as I'm writing this down, I realize that I miswrote up here. So let me correct this up here. That doesn't, what I just wrote is correct, but these were incorrect. So let me correct that right now. I apologize. This one right here is 0.560142. This one is 0.43, let's see, 9858. Okay, so I apologize, but plugging this into the formula, we do get the p tilde that's shown here, 0.56004. I was looking at the wrong line in my notes. Not surprisingly, p tilde is very close to p hat, and that happens when n is large. Next, we have to get the margin of error. The margin of error is going to be the complicated construction z times the square root of p hat q hat over n plus z squared over 4n squared divided by 1 plus z squared over n. And then we plug this into the calculator very carefully, and we get 0.0205. So the final answer is going to be to 4 decimal places, 0.5600 plus or minus 0.0205. And that is the 95% confidence interval. A few people asked me in class why these numbers are so small. After all, for problem number 47, the answer was 8 plus or minus 1.4 or so. For problem number 50, the answer was 231 plus or minus 3. So the question is, why were we getting such small numbers here? We're getting small numbers here because this is a proportion problem. And so both numbers have to be between 0 and 1 because they're proportions. They have to be between 0 and 100%, or written as a decimal somewhere between 0 and 1. So these numbers are small, and 0.02 is indeed very small, but that stands to reason because we had a pretty good size sample of size 2,253. Okay, for part B, the question is, what sample size is required to be guaranteed a confidence interval that has a width of at most 0.04? Now, before doing this problem, you notice that this one here has a width of about 0.04. The width here is 0.041. The margin of error is 0.0205, and so double that is the width, 0.041. So the answer that we get should be bigger than 2,253. I need a bigger value of n to get a smaller width, but it shouldn't be too much bigger than this. So that's a tip as to, how plausible the answer is when we come out the other end. Okay, so to do this, we derived this formula in class, and I'm not particularly big on memorizing formulas, but this one I think counts. The formula goes n is equal to z squared times 1 minus w squared over w squared, where w is the width. So in our case, 1.95996 squared times 1 minus the width, 0.04 squared, divided by 0.04 squared. Now I'm going to emphasize this. This is the width, 0.04, so that the margin of error is half that for 0.02. Then plugging this into the calculator, let me do it down here, we get 2,397.07. And for a problem like this, we always want to be safe, and so I'm going to round up so that I should take a survey size of 2,398 to make this happen. So even though if I round it, it would go down, here I want to be safe to make sure that I have a sample that's big enough to make sure this happens. And so even though 0.07 is, I would typically round down, we're always going to round up to be safe. So we get an answer of 2,398. Not surprisingly, that is bigger than the original 2,253, but it's not much bigger than 2,253. Okay, so that's 51A and B. Problem number 52. For 52, I assigned part B and C. Part B, find a 90% upper confidence bound. Now, if you can look at the phrasing of the question, it actually asks for a confidence bound on the standard deviation. That was unintentional, and I think everybody basically ignored that in class, and so we're going to ignore it here. So we're going to change the phrasing of the question, calculate a 90% upper confidence bound for the mean of the arsenic concentration distribution. You actually can do this for standard deviations as well. We're skipping that section of the book, however, so I'm not holding you responsible for that. Okay, so 90% upper confidence bound. So the form of the upper confidence bound will be mu is going to be less than, I want an upper bound, x bar, plus, now for this one we have a small sample size of size 5, so it'll be a number off the t distribution, times s divided by square root of n. Now what number t do we use? Well, we have a 90% confidence bound, and so it's a one-sided picture, so I have a different looking picture than I had before. And so we have 0.1 over here. And so I find the 90th percentile for the t distribution with 4 degrees of freedom, or else I use the 0.1 column in the table, and so I get the answer of 1.53321. Okay, so mu is less than x bar, which was given to be 24.3, plus 1.53321 times s, which is 4.1, over the square root of 5, using the numbers that were given in the problem. And so using the arithmetic, we get mu is less than 27.1112. And using the significant digits in the problem, we'd probably say mu is simply less than 27.1. Okay, so that's part A. Part B. Part C asks for predict the arsenic concentration for a single water specimen in a way that conveys information about precision and reliability. And in class we discussed that this again is subject to engineering judgment, but it's basically a prediction interval, and I left it to your judgment as to what level you wanted to use for making the prediction. So for the purposes of doing this problem, I'll do a 95% prediction interval, and the formula is going to be x bar plus or minus a number off the t-distribution times s times square root of 1 plus 1 over n. So the square root of n part is different. Here I have square root of 1 plus 1 over n, which is different looking than what we had for the confidence interval. So drawing the picture, here we have a picture that looks like the ones we've had earlier in this video. 0.95 in the middle. I have a t-distribution with 4 degrees of freedom. And so I have the same critical value, 2.77645. I have the same critical value that I had in problem number 50, and that's because I chose 95% for both problems. Okay, so we use the numbers here. We have x bar is 24.3 plus or minus 2.77645 times s 1.53321 times the square root of 1 plus 1 over 5. Now let me make a comment about this. N is still equal to 5. We have taken 5 previous measurements, and the issue is what's the next measurement going to be. A few people in class had the misconception that n was equal to 1. That's incorrect. N is still equal to 5, and I'm using this information from the 5 previous to predict the next one. So n is still equal to 5, just like before. And so finally we get our prediction interval, 24.3 plus or minus 12.47. And I'll round it up to 12.5 so that I have the same number of significant digits. This is a very wide prediction interval, not surprisingly, because it's I have a very few measurements, only 5 of them. I would have something significantly smaller if I had a bigger number of measurements. Okay, finally, question number 55. For question number 55, I want to point out we're trying to predict how many books are necessary to get the desired accuracy. I want to point out that 55, we should not use the same formula that we use in 51. This problem concerns the average force. So I have to deal with the standard error for an average. Problem 51 dealt with a proportion, so I'm going to be using a completely different formula than what I used in problem 51. Also in problem 51, what's given is the margin of error. So 0.1 pounds is given to be the margin of error in problem 55. By contrast, in problem 51b, what was given was the width. So just keep that in mind. 0.1 is equal to, it's 95% confidence, so the formula goes z times sigma over square root of n. Okay, and so we have 0.1 is equal to, now it's 95%, so it's going to be our friend 1.95996 again. Sigma is given to be 0.8 divided by square root of n, and then it's just a matter of doing algebra to solve for n. So I get n is equal to 245.8, and as always we'll round up. In this case, rounding is the way it would go typically, 246. So our answer is going to be 246. There is a formula in the book. However, be careful when using the formula in the book. The formula in the book works when you're given a width. So the width of the confidence interval here would be 0.2 pounds, twice the margin of error. So if you're going to use the formula in the book, just remember that the formula in the book is for you input the width to get the value of n. You do not input the margin of error. So this is one where I really recommend just simply knowing don't memorize formulas. You've got the margin of error, which you know very well, and then it's just simply a matter of solving for n for this problem.